In this video, we're going to look at exponential functions. This is section 1.7 from your book. Now, exponential functions are of the form, well, they look like this. In our little blue box, it says an exponential function whose base a is defined for the following real numbers x as being f of x equals a to the x, where a is greater than 0 and a does not equal 1. So let's substitute some values in. In example 1, it says, let f of x be 3 to the x and evaluate the following, f of 5. Here, of course, it wants to substitute a 5 in for x, so we'll find out what 3 to the 5th is. And 3 to the 5th is 243. Here it wants us to substitute in a negative 2/3. Our calculator will do this for us. 3 to the negative 2/3. When you do this on your calculator, you may want to type that negative 2/3 in a parenthesis. So you'd use the 3 caret button and then a negative 2/3. So it knows that this whole quantity is the exponent. And you should get about 0.4807. Let's look at what these look like as you graph them. Now, in example 2, part A, we have f of x equals 2 to the x. Now, this base we call 2, and it is greater than 1. So when you have a function like this, it's going to be increasing, and it will look like this. A couple points on here. It's going to look like that. You can get your graphers or Desmos to graph that, or you could use a table of values. If you'd used a table of values for x and y, which is the same as f of x, and plugged in some negative values here for x as the exponent, here you get 1/4, 1/2, 1, 2, 4, and 8. So this leads to the ordered pairs a negative 2 and 1/4. A negative 1 is at 1/2, 0 is at 1, etc. Now here, our base is 1/2 in B, where we have g of x equals 1/2 to the x power. We're going to have a function that looks very similar, except it's going to be decreasing. It's still going to be a curve, but instead of increasing like 2 to the x, 1/2 is going to be kind of exactly the opposite, the mirror image of the prior, but it'll be decreasing. So like a negative 2 would be up at 4, negative 3 would be up at 8, which was vice versa here. At a negative 1 would be at 2, and it will look like this. If we plug the values in for x, you would see, oops, it's a curve. And it never touches the x-axis, unlike my graph there. So qualities of exponential functions. They're always continuous, which means there aren't any jumps or places where you pick up your pen when you're graphing it. They're always 1-to-1, which means for every one x value, you'll only have one y value. The domain is negative infinity to positive infinity. The range is 0 to positive infinity because they are always above the x-axis. If a is greater than 1, as we saw in our first example, 2 to the x, you have an increasing function. If a is less than 1, you have a decreasing function. And this should actually say between 0 and 1, because you can never have a negative base. The horizontal asymptote is the x-axis, y equals 0, and the y-intercept on these functions is 1. Here we have a graph of a bunch of different examples. Here's 1/2 to the x as we just graphed it. 1/3 is in green, 1/5 is in blue, and 1/10 is in yellow. 10 to the x is in purple, 5 to the x is in blue, 3 to the x is in black, and 2 to the x is in red. So you can see when your base is between 0 and 1, you have a decreasing function. And when your base here is greater than 1, you have that increasing curve. So this says that same thing again. When a is greater than 1, you have that increasing function with the y-intercept of 0, 1. And when a is in between 0 and 1, you have that decreasing function. Now, in example 3, it wants us to graph these translated. We learned before, the way you translate graphs is you look at what's going on near the x. So here, my function that we'd be starting with is f of x equals 2 to the x, which we graphed above. Here we want 2 to the x minus 2. So since this minus 2 is where and kind of connected to where the x is, what that means is it's a horizontal translation, and it would be 2 to the right. So this is going to move that graph from above 2 units right. 2 units to the right. So instead of having these points from the graph of 2 to the x that we had above, they're all going to be slid to the 2 to the right. So that vertical intercept, which was at 0, 1, is now going to be at 2. The point that was at 1, 2 is going to be moved over 2 to the right here. And this graph, this should be, anyway, like this. Here, since in B, where we have f of x equals 2 to the x minus 4, since the subtracting of the 4 is not in the exponent with the x, this is going to be a vertical shift 4 down units down because it's minus 4. So instead of the points that we had here for 2 to the x that we graphed above, they're all going to move down 4 units. So at 0, 1 is going to be moved down 4 to 0, negative 3. And these will look, let's see, that's right, like that. All right. A word problem that you might have using an exponential function might look like this. It says the amount of money A to which the principal P will grow after T years at an interest rate R in decimal form, compounded n times per year, is given by the formula A equals P times 1 plus R over n to the nt power. Let's reiterate. This is the amount you have at the end. This is the amount you start with. R is the interest rate, and n is the number of compounds per year, and t is the number of years. So suppose that $100,000 is invested at 6.5%. Compounded semi-annually means twice a year. Find the function for the amount to which the investment grows after t years. So for A, it wants us to find that amount using these numbers in my function. So it told us that my P, my principal, was $100,000. That, and we would be multiplying that by 1 plus my interest rate is R, which was 6.5%. So we're going to write that as 0.065 over 2 for semi-annually to the 2 times t. So this will give us the amount of money we have after t years. B wants us to find the amount in the account after 0 years, 4, 8, and 10 years. So we'll be plugging those numbers in for t respectively. I'm going to write that down here. All right. So we're going to substitute in the 0, 4, 8, and 10 for t here. Now, when you do this, I would make sure that you put a parenthesis around that exponent so that you know that it's putting both numbers in the exponent. Here, you don't even really need to calculate it because 2 times 0 in your exponent is 0. And we recall that any number taken to the 0 power will be 1. So this is like 100,000 times 1, which is 100,000. Now, if we plug it in here for 4 years, we'll take this to the fourth power. And remember, put that in parentheses or simply take it to the eighth power, and you'll get 129,157. And since this is dollars, let's go ahead and round to the nearest cent. So that'd be in 75 cents. Now, similarly here, we're going to take it to the eighth power. So plugging that into our calculator, we're going to get 166. This is dollars. 166,817 and 25 cents. And then we'll plug in 10 and get 189,583.79. $83.79. All right, so here it wants us in part C to graph this function. Now you can graph this function using your calculator, but when you do, you want to be aware of your domain and range. Here we looked from 0 to 10 years, and we had Y values that ranged from 100,000 to almost $200,000. So you'd want to make sure your X and Y windows only had positive values. Your X and Y values were only talking about positive values, and that they went up to the correct amount so you can see the function. Now, this should be an exponential function, so it should be a curve that looks like this. At 0 years, we're at 100,000. At 4 years, we're at 129,000. It's going to be right about here. At 8 years, we're at 166,000, so 8 years would be here. 166 would be right in here. And then at 10 years, we are at 189,000, which is going to be up here. This almost looks like a line, but it would really look like a curve if we had a greater designation of greater distance between these values. Right. So another exponential value that we often use is E. E is what happens when you get to compound continuously. So the natural exponential function is the exponential function f of x equals e to the x. Now, E is approximately the number 2.72. So that's why my exponential function E here, above graphed in red, is going to be between the exponential function y equals 2 to the x and y equals 3 to the x, because E is again about 2.72 to the x. So let's evaluate each of these expressions and round them to 5 decimal places. The first problem on 5a says e to the third. So if we substitute 3 in as the exponent, we're going to get about 20.0855. It says round to 5 decimal places, so 554. Here it wants us to find 2 times e to the negative 0.53. Let's see what you get for that. So that one should give us about 1.17721. Here's the number after the 0 was a 9. Here we have the graph of e to the x would look like that. And e to the negative x would, of course, be the same as y equals 1 over e to the x, because that's what a negative exponent does, is it flips the base, which, of course, would be a decreasing function because this value is in between 0 and 1. All right, I hope that is a good refresher on exponential functions. In our next video, we're going to look at logarithmic functions. Thanks for watching.